Good evening to everyone. I hope screen is visible to everyone. Yeah, good evening. So I think we can start now, okay? Good evening to everyone. Myself, Swapnil Balasab Godke, doctoral research scholar at the Indian Institute of Technology, Roorkee. So currently I'm working as a teaching assistant for the development and applications of special concrete with Professor Sudhir Mishra, sir. So I hope your problem regarding to the assignment 4 has been resolved, right? Week 4 sessions assignment has been, the problem has been now resolved. Yeah, new assignment has been made. Okay. So I hope you are going through the week 6 lectures. So we will shortly or briefly will see the recap of the week 6. So in the last lecture, we saw one video regarding to the rheometer, how test has been done. So different types of rheometers are used to find out the rheological properties such as yield stress and plastic viscosity. So now we'll see in detail what is the rheology actually and why it is necessary to understand the rheological characteristics of the mainly flowable concrete or self-compacting concrete. So basically rheology is the study of flow behavior and is normally applied to the fluid materials or materials that exhibit a time-dependent response to the stress. Time-dependent response in the sense with the time hydration increases, the concrete material will get steep. So that is the time dependent response of any type of cementitious material. But if it is a flowable material and then we are understanding the time dependent response, then we have to understand the rheological properties such as yield stress and plastic viscosity. So fresh concrete is a fluid material and its rheological behavior affects or even limits the ways it can proceed or place. We saw the slump test. Slump test is a rheological measurement, but it doesn't give any type of rheological response, such as it indirectly we can say the rheology slump test can be given a plastic viscosity response or the yield stress response, but direct parameters such as plastic viscosity and yield stress we are not getting the value from the slump test. For that purpose, we have to go with the ichorrheometer or any type of rheometer. So flow behavior of concentrated suspensions can help us to measure and understand the behavior of fresh concrete. So, how to measure the flow of the concrete or rheological properties? Flow is typically measured using the shear parameters of stress and strain rate. Shear parameters means whatever the concrete material, whatever the cementitious material we have, will provide some rotation or some shear torque will provide on that over that one. That is called as a strain rate, and we'll measure stress. How what is the stress required to break down that internal what we call bonding, then which normally obtain direct viscosity measurement torque and flow rate in rheometers. So viscosity is a representative parameter used to assess the flow behavior and it is defined as the ratio of stress to strain rate. Once we get the torque and strain rate strain value from these are the raw data obtained from the any type of rheometer. Once we plotted that data, we use the some of the equations, that is we call the transformation equations, with the help of the Bingham model, Herschel Berkeley model, or modified Bingham model, and with the help of that one we'll calculate the yield stress and plastic viscosity. And what is the uh, plot we have? Stress and strain rate, slope of that plot indicates the viscosity, that is also called as the plastic viscosity. It is the resistance to the flow. We saw why we have to understand the in the case of self-compacting concrete, because we required deformability of the paste, at the same time we require adequate viscosity which will resist the segregation of the material. So that's why rheology is a very important part in the self-compacting concrete also. So how much amount of coarse aggregates, what is the size of the coarse aggregate we can use into the some of the flowable concretes, that has been carried out or that has been find out with the help of this type of test. In this test, like especially near the reinforcement bars, how concrete will flow and it will block because of the obstruction of the flows. So that we'll find out with the help of this test. One cylinder will be there which is having the diameter of 100 mm. This is the type of piston which will have a certain amount of the diameter of holes, such as 5 mm, 10 mm, and 15 mm. Whatever the type of aggregates we are using, we can use that type of hole into the piston. We have the we have the mortar in this cylinder. We press the piston and we'll see what amount of when the mortar is easily flowing through that holes. We can say the amount of fine aggregate or coarse aggregate, especially coarse aggregate, is sufficient or it's flowable through that mix. When the mortar is not flowing through the piston's hole and it is blocking that holes, that is called as the maximum amount, or it is not allowing the concrete or mortar to flow that coarse aggregates. So if we, that possibility of blocking, and this is sand volume. So if you see diameter of the 10 mm of the particles, the 44% of sand is the critical value. Beyond that one, the continuous blocking is observed. Similarly, different types of diameters, the plot has been given critical volume of sand for blocking and the ratio of holes diameter to the average size of sand. So to find out the amount of sand or size of the sand or aggregate, this type of test has been carried out. Another test is that water retention. We saw the slump cone, right? What is the dimensions of the slump cone? Anyone? 200 at the bottom. Or top height how much? 30. Okay, and top diameter? Hmm? 100. Top is 100. Yeah, top is 100, bottom is 200, and height is 300 mm. Right? That is the our original slump cone. This is the mini slump cone we called as. It has the top diameter is 70 mm, bottom diameter is 100 mm, and height is 60 mm. So we what we'll do, same procedure we'll do. We'll put into the this table or this platform into the center. We'll without compaction, we'll pour the material into in that one, and we just lift the this mini slump cone, and the automatic flow of the concrete over the surface will allow. Then we'll measure the larger diameter first, and then perpendicular to that one another diameter, and we'll get the average of that diameter. These two things we can do. Then what we have to calculate the relative flow area. So relative flow area, final area, means this is the whatever the diameter, average diameter will get it from the flow. That based on that diameter, we'll calculate the area, that is final area. We know initial diameter, that is 100 mm. That will called as initial area. Okay. So final area minus initial area upon initial area will get the relative flow area without providing any type of compaction or without giving any type of blows to the table. Why we have to calculate this one? Because we have to understand what amount of water retention is carrying that particular matrix of the concrete. So if you see volume of water to the volume of powder. Powder we saw in the last lecture also. Powder means not only cementitious parts. Cement plus fly ash, silica fume, or any other supplementary cementitious material or mineral admixture. It is together. It is called as powder content. So volume of water versus volume of water to the volume of powder versus relative flow area. We plotted that graph, and we got this type of linear lines. So can anyone tell me what it indicates, this beta P and beta M? Just you have to find out. Here it is zero flow, right? Means concrete is more stiff. Here, as we are increasing, flow area is increasing. The this because you can see volume of water to the volume of powder ratio increases. Means ultimately either powder content decreases or water content increases. So if it is water, suppose you consider water content is increases, obviously flow will get increased. That's why flow area is also goes on increasing. So what is the zero flow area indicating? Can anyone, any guess? based on the visual interpretation, what you can observe, what you can say, what beta m that is related to the mortar and if p is related to the paste beta p, what it indicates actually at zero flow. It indicates zero flow means already certain amount of water is there, right? Water is there, but that is not allowing water water retention. That is water retention because zero relative area for mortar or paste thus means no deformation. Deformation is not observing. We are not observing any deformation. That's a zero flow area. At the best express, this water content defined as the water retention in the mortar or paste. That is the water retention. Once the critical value of the water retention over or achieve, after that only flow started. Right? Excess amount of water only allowing to the flow. So that's why this value is also important, beta m and beta p. And what EM, the slope and your paste graph slope indicates, it indicates the sensitivity of that particular flow. Okay. So how we have to do this to test? You understand what is the purpose of this to test? One is the understanding the amount of sand content and coarse aggregate content, and another one is the how to identify the water retention of the mortar mix. So basically, flow behavior of any cementitious system is a suspension cement. Suspension means solid particles either in a disperse or either in a flocculated. Disperse in the sense they have a certain amount of distance between the each particles, and flocculated in the sense closely together. So if you want to see volume of solid particles, it is Vs. If the volume of solid particles increases, automatically crowding of the particle increases, which increases the viscosity, right? Suppose you have 100 ml of water and you have 5 gram of cementitious particles in that one, and then another beaker you have 100 ml of water and 100 gram of cement in that one, which will have the higher amount of viscosity. Which beaker fluid will have higher amount of viscosity, which is having higher amount of cementitious content, right? Here I am giving an example of cement content, but any type of solid particle, if amount of concentration is high, then it will responsible for the higher viscosity because large amount of force required to get the flow or large amount of resistance is available to the flow, right? Viscosity is basically a resistance to the flow. Degree of agglomeration or flocculation. Flocculation in the sense certain amount of particles will be there and that particles closely bond together with the help of certain amount of force. That force may be the van der Waals force, that force may be the chemical bond force. So the van der Waals force may be broken down with the help of certain amount of shear force. But if it is a chemical bond, means due to the hydration, there is a larger chances which will not be the irreversible, right? Certain amount we can reversible, but larger amount we cannot be irreversible. So other influencing factors flow behavior are temperature and pressure. These are the weathering factors. When we are going with the self-compacting concrete, 3D printing concrete, or flowable concrete, shotcrete concreting, these are some of the flowable concretes. So in that aspects, if we are going print or if we are using that concretes very humid or very high temperature zones, and then we are using in same concrete we are using into the colder region, both are having a different behavior because of the higher viscosity. You see this sentence, liquids with the higher viscosities generally have a greater temperature sensitivity. Very important sentence. Whichever the material which has the higher viscosity, that has the greater temperature sensitivity. So that's why we have to be take care regarding to that weathering factors also. So viscosity increases with increase in the pressure, though the changes are minimal at atmospheric pressure. Then flocculated suspensions. Which type of suspension we call flocculated? The particles smaller than 1 micron in diameter could result in aggregation or gel formation. In the case of flocculated suspensions, internal forces are fairly weak, and stress at which breakdown of flocculated network is called yield stress. So, in which case, just now I said, in which case the internal forces are fairly weak. Which type of force? Which type of bonding? Van der Waals force bonding. You can read much detail about which one? Hydrogen bond. Yeah, but hydrogen bond will not possible in this case. Most of the like cementitious particles will be either in the van der Waals force or maybe due to the hydration that CSH bonds will form. Yeah, that is chemical bond. So, and one another important sentence is that the stress at which breakdown of flocculated network is called yield stress. Whatever we will measure from the rheometer, na, that yield stress is basically the breakdown of flocculated networks, right? Then dispersion suspensions usually show Newtonian behavior at low solid concentrations. Newtonian behavior, you know Newtonian behavior? Anyone remember? Yeah, what it says, shear stress is directly proportional to the shear strain. Yeah, because it starts directly from the origin to the linear line. So why disperse suspension shows Newtonian behavior? Because sometimes solid concentrations are lower. That's why it shows Newtonian behavior. But if higher solid concentrations are there, they show considerable yield stress and exhibit plastic behavior due to crowding of particles. So last time also we saw one of the example. Daily use example is toothpaste, right? Toothpaste. If you open the open the toothpaste and we are just keeping it, it will not come automatically out of it. We have to give some pressure, right? Or some force we have to press. That force is initially it's required as the initial yield stress, and that initial yield stress is that material is we called as Bingham material because it we have tau zero and then it is shows the linear region. That toothpaste is the example of the Bingham material. In the case of dispersed suspensions, the distance between the particles are high. That's why no interparticle forces are available. So basically, we have to understand the difference between the flocculated suspensions and dispersed suspensions. In the flocculated suspensions, bonding are there, but it is a weak bonding. And dispersed suspension, there is a no at all, not at all interparticle forces are available. Further, in the case of cement pestes, disperse system, it is non. If it is a higher solid concentration, it is non-Newtonian system. And what are the physical factors affect? Water cement ratio, cement grain shape and size, chemical factors, cement composition and its structure, modification due to hydration, mixing and measurement conditions. Can anyone tell me what happen if water to cement ratio increases? The flow will, what will be the response of the flow in aspect of yield stress and plastic viscosity? Can anyone? Right, because flow will be more, obviously resistance will be less, so yield stress will get, plastic viscosity will get decreased. And because of the higher amount of water, whatever the solid concentration which are already have, that will convert from disperse medium, right? So yield stress will be less. So increasing the water to cement ratio, both parameters will get decreased. Similarly, cement grain shape and size. Finer the material, higher the inner or hydration mechanism will happen. Irreversible breakdown will be possible. So that's why very fast setting will happen. So that's why yield stress will get increased. plastic viscosity will also get increased, and cement grain shape depend on the spherical particle or cubical particles, that one. And chemical factors, composition of cement, like faster setting cement or low, suppose any other type of cements are there, sulfate reacting cement. Based on that chemical factors also rheological parameters affect. Then hydration is one of the mechanism which is irreversible. And mixing and measurement condition. Do you know, although we have the rheometer type of rheometer to measure the rheological parameters, but there are different types of rheometers. And if you measure, suppose you are using ICAR rheometer, and another one is suppose you have the different company rheometer. I am not recalling company name at this time, but so if you measure same material, you will have the different result with the two types of rheometers. So that's why you have there is a necessity to mention the equipment name and the equipment testing protocol while reporting the result of the rheological parameters, because there is no standard protocol or no standard code available to measure the rheology. Similarly, mixing, if you are mixing the same proportion of the mix with the 100 RPM concrete mixer, and then you are mixing same material with the 200 RPM, then obviously both the material will show different rheological behaviors, because shear history is different. Shear history in the sense, whatever the mixing you are doing, shearing of the material, if you are mixing with the higher speed, there is a possibility to have the higher hydration or higher heat generation. That's why the material will get stiff as early as possible and it will show higher yield stress and plastic viscosity at the time of testing. So both the parameters are very important, mixing and as well as measuring conditions and measuring equipments. Further, normally assess using shear rheometers generally operate in rotation. Will rotate, that is, will give the shear and measure the torque and rotational speed as a raw data as a result. Then we'll plot that data and then we'll go for the further analysis. Two fundamental types of rheometer generally used: coaxial cylinder and parallel plates. Sample generally sits between the gap between these two types of equipments. Rheometers either control, this sentence is important, rheometer either control the stress and measure the strain rate, or control the strain rate and measure the stress. This type of arrangement we are also using one of the equipment in testing. Can anyone guess what is that equipment? What it does, rheometer, what does actually, it control the stress and measure the strain rate. Then control, another aspect is controlling the strain rate and measuring the stress. Similar we can do in CTM. If you remember, we have a load control and displacement control, right? In the CTM also we will do load control test or displacement control test. Here is similar. Here is a stress control and strain control. Similar manner we or similar mechanism we can use it. These are the two types of rheometer. The coaxial cylinders. This is the gap between the cylinder and the cylinder. This is the one of which rotates. Out of which either outer part will rotate or either inner cylinder will rotate. And this is the torque measuring device. Similarly, these are the two plates above each other. There is a gap between the two plates, and this is the black part is the material in which between that gaps. So that shearing of that plates measure the torque and rotational speed. So if we have a stiff material and if we have little bit flowable material, so in which type of rheometer we can use the stiff material and in which type of rheometer we can use flowable material? Can anyone? This is the parallel plate rheometer, two plates above each other, and there is a gap between. So if we are having the too much flowable material, the material will not able to stay in between that plates. So that's a little bit stiff material we can have in between that parallel plates. So whatever the stiff material, If you want to measure the rheological properties, we can use the parallel plate. And too much flowable material, we can use the cylinder type of rheometer or coaxial type of rheometer. This is the very common. We have already seen this one in our bachelor's in the fluid dynamics. So you see the Newtonian behavior, which is shear stress versus strain rate. There is no effect of that or direct relation between the shear stress and shear rate. Bingham plastic, initially you have to give certain amount of stress, then only the flow starts. That is called as Bingham model. Or we saw example of toothpaste. Shear thinning or shear thickening. What is shear thinning means when you are increasing the strain rate, means rotation or whatever the strain you are giving. If you are increasing the strain rate, stress goes on increasing. Similarly, shear thickening in opposite in that way. So Bingham model. So Bingham model you see tau is equal to tau zero. This is the tau zero. This intercept is called as tau zero. That is called as initial yield stress plus eta p. Eta p is the plastic viscosity, which is the slope of this Bingham plastic graph, and gamma dot is the shear rate. Then another model is power law model. That is tau is equal to k into gamma dot raised to n. N is called as a flow index, and flow index will be how we'll calculate that one. That is like a fitting model. If this model you fit, you will get the n value. That fitting coefficient or flow index we can call it as. So tau zero is the yield stress, k is the consistency in this one, n is the power index, eta p is the plastic viscosity, and gamma dot is the rate of shear strain. Okay. So anyone have any doubt up to this? Okay, no doubt I think. Okay. So what are the common issues while studying the flow behavior? It's not that much easy to understand the flow behavior or to measure the flow behavior. Basically, into the because there is a rheometer already available in other domain also, polymer, then whatever the fluid materials into the industry are available. In that one, rheometers are already used. But in the case of cementitious material, what happens due to the too much factor dependent, such as weathering factors, temperature and ambient conditions, humidity, and shear, what we call the hydration mechanism, it's somewhat difficult or challenging to understand the actual rheological behavior. So, what are the common issues? Segregation of cement paste. It is more likely in plastic or pseudoplastic suspension at higher strain rates. If you are having cementitious mix, you are providing certain amount of shear rate, and then you are increasing the shear rate for another material. Obviously, both are giving different results because shear rate or strain rate is very important. If you are mixing with the higher rate, you will get the different values, and there is a possibility with the higher strain rate, the larger particles will get separated from the matrix. That is called as segregation of cement paste. Segregation is likely in flocculated suspensions and at very high concentrations. So, what author says, cement paste follows a combination of Bingham and pseudoplastic behavior known as Herschel-Berkeley model. And this is the equation we saw. So, what is the pseudoplastic behavior? Shear thinning behavior. We saw in the last plot. This one. Pseudoplastic behavior is a shear thinning behavior. And what we called this one? Shear thickening behavior. What it is called? Anyone remember from the fluid mechanics? Dilatant behavior. What it's called? Dilatant. When we are using a superplasticizer, cement paste shows a Newtonian behavior at low concentrations and plastic behavior at high concentrations. So, what superplasticizer does? We saw in previous 2 3 lectures also we are We are seeing superplasticizer uses since first week. Then can anyone tell me, when we are adding water into the cementitious matrix or any concrete matrix, so it will start the hydration, it will start the mixing process. So what will happen when we are adding the superplasticizer? Anyone? No one? Right, right. Correct answer. So we'll have a certain amount of trap water inside the cementitious particles. So when we are adding the superplasticizer, that will create the repulsion between the cementitious particles. So that repulsion will release that trap water into the cementitious particles. So that trap water will responsible for the giving the flow of the material and reducing the yield stress and plastic viscosity. And that's why it shows the Newtonian behavior. But when there is a low concentrations of the cementitious particles, but when we are having the higher concentration of cementitious particles, that will show the plastic behavior. Okay. Then, while assessing the flow behavior, there could be some hysteresis in the stress. When strain rate is increased from 0 to higher values and brought to 0 after reaching peak. So, what it actually indicates? So, basically, first of all, if you remember from the last lecture, one video we saw, in that one, that the video says one test is stress growth test and another test is flow curve test. So in the case of the flow curve test, what will happen? He mentioned about the hysteresis stress. So we have seven number of points. Suppose I'm discussing with respect to the ICAR rheometer. So we have the seven number of points, each having the different rate of shear. Suppose maximum rate of shear is zero point 0.5 rpm, and then it is minimum is 0.05 rpm. So in between that one, it is divided into seven equal parts. So zero point 0.5 rpm at certain time or sometime it will rotate it and will give some amount of torque. Then for next point it will rotate for some time and then will give next torque. Similarly for 7 points it will rotate for seven times each point and then will give the some torque. Then we plotted or we fitting that line, will get it flow curve. Once we are going from the zero point 0.5 to 0.05 and 0.05 to, oh sorry, zero point 0.5 to 0.05 and then 0.05 to zero point 0.5, opposite each other, minimum to maximum and maximum to minimum. So what will happen when we are going to minimum to maximum or maximum to minimum and then you are coming back, there will not always possible to follow the same path, right? Because of the hydration there is a certain amount of cementitious particles which will not get breakdown. So that's why if it is not following the same path, it follows first suppose this line, then it will go back, come back to the different path, and whatever the areas between the two lines, it is called as hysteresis area, and that indicates the thixotropy of the material. What it indicates? Thixotropy. If you see simple example, not from the rheometer perspective, you have a certain cementitious mix or concrete mix, right? You mix it, you prepare it as some flowable or little bit workable concrete. Then you kept it for half an hour or 1 hour. Certain amount of setting will happen. Then you come back. Then again you put that material into the concrete drum or mixer. Again you mix it. Do you get it same flowability whatever we have actually at the time of preparation? Will you get it? No. So that is called as the that flow curve will not follow the same path. Again, if you are providing the stress or shear rate, So that is called as a hysteresis, or that is called a thixotropy. That is the nature of the cementitious material, which because of the hydration mechanism, and that reflects the equilibrium between the microstructure and the strain rate. Denotes that material is undergoing irreversible structural breakdown due to shear. So we have to be remember that there is a 90 or there is a 100% possibility it will not follow the same path. There is always have some certain amount of thixotropy in any cementitious material. It may be minimum or it may be maximum, depend on the your constituents of the material. So we saw cementitious paste. What about the concrete? So flow behavior must be described using yield stress and plastic viscosity due to Bingham nature. In the case of concrete, due to the coarser particles, there is a possibility to settle down due to gravity, and segregation is more likely to happen during shear, right? Because as the concrete is there, if you are providing the shear or shear rate, there is a high possibility to have a segregation. That's why another problem is that slip. We have the container. If you saw into the last video, we have the container, large container, and we are providing to the vane shear. When we are providing the vane shear, there is a possibility the material itself, if it is stiff, the material itself totally rotate. If it is not rotating inside the material, total material rotate against the cylinder. So that's why surrounding the cylinder there is a strips that is called aggravated strips. That aggravated strips will be there, which will not allow to material, whole material will flow, or whole material rotate into the cylinder itself. Only the part of the vane which is rotating, that will only break down the material. So these are the problems observed into the concrete. So that's why we have to provide the minimum shear rate in the case of the concrete, which will mimic the actual procedure or actual protocol of the mixing. So concrete exhibits plastic behavior. If you see, this is the torque versus angular velocity, that is rotational speed. We get the data, we plotted, and we'll see this is the intercept we called as tau zero. Slope of this graph, we'll get it as a plastic viscosity, that is eta p. We have the shear rate, at what shear rate we have rotated that material, that is gamma dot, and we'll get the whole equation for that particular material. Because in concrete there is a wide range of particle sizes are used, so there is a more complex nature of the behavior we'll observe. So flow depends on the concentration of particles, extent of flocation of cement particles, and flocculation is only important in the case of cementitious particles. It will not happen into the inert particles, such as the fine aggregate or coarse aggregate. And ranges of strain rates during testing should be low to simulate the actual field conditions, mixing, transporting, placing, and finishing. Very important sentence. Apart from that one, why we have to go for the low strain rate? Because high strain rate, there is a chances to have the coarser particle to get settled down. Okay, so that's why we have to go for the low strain rate, and it will also follow the or simulate the actual field condition, mixing, transporting, placing, and finishing. So apart from that one, what are the different types of factors affecting water to cement ratio? So increasing the water to cement ratio results in a lower yield stress and plastic viscosity. We saw because of the dispersion of the particles, trap water will get released, which will be responsible for the increasing the flow, and at the same time, due to increasing the flow, yield stress and the plastic viscosity will get decreased. Second, total aggregate content. So increasing total aggregate content results in an increasing plastic viscosity. Can anyone tell me how it will possible like aggregate content increases the plastic viscosity? Anyone? Okay. Second one, this you can see concrete with the river gravel due to its much rounded and smoother surface has lower viscosity and yield stress. Now you can tell me both the sentence you can read, and now you can tell me how it increases the plastic viscosity. See, one factor is that concentration of the coarse aggregate particles, right? If the concentration is very high, the more force or more resistance will be there to get the flow, and less amount of mortar will be available which can carry that coarse aggregates with the flow. So that is called increase in the plastic viscosity due to the concentration of coarse aggregates. But if you are using, instead of the rounded particles or rounded coarse aggregate, if you are using the angular particles, what will happen? That will create the internal friction, because it is interlocking will happen into the angular particles, and that angular particles will increase the plastic viscosity due to the internal friction between the coarse aggregate particles. So main reason is that interparticle friction to increase in the plastic viscosity. Rounded particles will be easy to flow, which have a less amount of internal friction. That's why lower viscosity and yield stress with the river gravel and rounded and smoother surface particles. Sand content, both yield stress and plastic viscosity follow an initially decreasing, followed by increasing trend with increasing sand content. The lowest yield stress and plastic viscosity occurs for a sand at of 38%. Now, if you see this sentence is totally subjective actually, because whatever the type of sand you are using, based on that one, this is whether it is 38% or whether it is more or less. This observation, according to this paper, whatever the sand they have used for that purpose only, they observe 38%. But if you are using different types of sand, whatever have the different types of gradation you are using, your value may get vary, and the result will also get vary. That yield stress and plastic viscosity parameter results. Admixture. Fly ash reduces both yield stress and plastic viscosity. We saw several times because fly ash is circular or spherical in nature. So that will be responsible for the increasing the lubrication and responsible for the increasing the flow. That's why reducing the yield stress and plastic viscosity. Super plasticizer, elapsed time. Elapsed time because as we are keeping the same material. Suppose now one more study is there in the rheological aspects. You have the concrete or cementitious material with the same rotating speed or shear rate. You are checking their yield stress. Suppose you are checking yield stress at 0 minute after the directly mixing the material, then 5 minute, then 10 minute, then 15 minute, 20 minute, 25 and 30. Similarly for 5 minutes gap. Because of the hydration mechanism, as we saw, there is irreversible part is there. Because of that one, each point, that is 5 minute point, 10 minute point, 15 minute point, you will observe higher yield stress because of the higher yield stress and higher plastic viscosity because of the increasing the hydration mechanism. That is chemical bond improvement. Okay, that's why it is called as time dependent yield stress. Up to this, anyone has any doubt into the rheology? Any part you have not understood? Once you go through the lectures, or if you are going through also, you will understand more. And whatever the part, if you are not understanding, you can ask. Or sir also suggesting one book, very nice book, that is Monter and Mehta. In that one, you will find out the details about the concrete. So I hope you have understood up to this one. That is the rheology part. This is the brief introduction of the rheology part. Then we'll move forward with the fiber reinforced concrete. Okay. Yeah. So most of you are well known about the fiber reinforced concrete, because nowadays it is very popular. People are using as a fiber reinforced concrete. So why we are having the need of fiber reinforced concretes? Because it our concrete has relatively low tensile strength, low energy consumption capacity. That is called toughness. Can you tell me what is the tensile strength value? We have a certain relation with respect to the compressive strength in the code. Anyone remember? 5,000 under root of FCK. That is Young's modulus, na? Okay, point 0.7, point 0.7 root FCK. And another is like one thumb rule is also there. What it is called? How much it is? One tenth of the, have you, yeah, one tenth of the compressive strength. You will, this is thumb rule actually. We call it as a tensile strength of the our concrete matrix. So these are the two problems. Already we have one tenth of the tensile strength compared to compressive strength. That is very low, low energy consumption capacity. So why we need tensile strength and why we need energy consumption capacity? That is called toughness. Because if you want to behave concrete perfectly into the flexural condition as well as into the earthquake loading condition, that is ductility point of view, we need these parameters more efficiently. That is called tensile strength and toughness. So what fibers do? Fibers may be the continuous fibers, long fibers, or it may be the short fibers which can disperse into the concrete matrix in a random orientation. Okay. So typical use of fibers in cement matrix: main is shrinkage control or shrinkage crack control, mechanical property enhancement, that is improving flexural performance, impact resistance, and alter the failure mode. It's very important. It alters the failure mode. We'll see how it alters. So, what is the difference between fiber reinforcement and conventional reinforcement? Fibers are generally distributed throughout the concrete, whereas reinforcing bars or wires are placed only in the predetermined locations. Because bars will provide only into the tensile locations, tensile zone of the concrete. Suppose we have the beam, we have the compression zone at the top and tensile zone at the bottom. So most of the bars we will have the into the bottom part of the beam. Forget about the curtailment and the tall things. Just we have the at the bottom. We don't have, if we are doubly reinforced, we are doing, even though we have the less number of bars at the top and the large number of bars at the bottom. But what happens if you are using the fibers? It will completely disperse whole the concrete matrix, and it will improve their mechanical property. So fibers generally short, discrete, and closely spaced, and randomly distributed throughout the matrix. Presence of fibers in concrete modifies the properties of the concrete. This is quite in contrast to reinforced concrete, because reinforced concrete does not modify the properties of concrete. It only modifies the tensile behavior of the concrete, or it will resist the flexural. It will give the flexural strength to the concrete. So obviously, it is possible to have fiber reinforced concrete used as a part of conventional reinforced concrete. Means you can use together. You have the bars also, and you can use the fibers also. So more effective use of fibers. You'll observe. So main factors that control the performance of the composite material are physical properties of the fibers and matrix, strength of bond between the fibers and matrix. Physical properties means length, diameter, type of the fiber. These are the physical properties we have to be understand, because all types of fibers will not behave equally or will not show similar performance or efficiency into the concrete matrix. So that part we also have to be considered. Strength of the bond between the fibers and matrix. We'll see how we'll measure the strength of the bond. That is also important, because if you have a fiber into the concrete matrix, maybe you are aware about the pull out test, right? We'll do for the concrete rebar. Rebar, steel rebar, we will do for the pull out test to see the bonding between the rebar and the concrete matrix. Similar manner, we also have to be understand how the bond is observed between the fibers and the matrix, because fibers are this short and the small in the diameter. That is very important to understand the bonding properties in between the fiber and the concrete matrix. Another aspect is that fiber volume ratio. If the fiber volume is low, moderate, and higher, that also affects the properties of the concrete matrix. So, what is the fiber volume? Ratio of the fiber volume VF to the total volume of the FRC. That is concrete, fiber reinforced concrete. At low VF, fiber volume, the addition of fibers contribute mainly to the toughness. And at a higher VF, the tensile strength of the matrix can be enhanced and the failure mode can be changed. So how much lower and higher the value we'll see into the next slide. Can anyone tell me what is the toughness? Actually, what it indicates into the load deflection graph? Anyone? Right. And will represent as a area under the load deflection curve. Right. So, but up to what point that we'll see. We cannot get whole area. We'll calculate up to certain displacement or certain deformation point. Up to that point only we'll measure the area under the load deflection curve, and that is we called as the toughness of that particular concrete matrix. So the properties of the matrix influences the bond with the fibers and the mechanical properties of the fiber reinforced concrete. Obviously, if we have the different types of the material constituents, we'll have the different bond properties. That's why FRC can be modified using mineral admixtures such as fly ash, silica fume, and metacolin. Because these are the mineral admixtures which will be responsible for the latter, giving the strain to the latter edge. That's why whatever the pores will be there, whatever surrounding even the fibers also, that will fill with the additional CSH gel and will give the more bonding. So that's why mineral admixtures are recommended to use into the fiber reinforced concrete. So classification, I am discussing about the classification. So low fiber composites, how what it calls low fibers, if fiber content is less than 1% of the total concrete matrix, that is called as low fiber composites, and that is mainly used to reduce the shrinkage cracking. If the fiber volume is between 1 to 2%, that is called moderate fiber composites, and it exhibit improved mechanical properties and can be used as a secondary reinforcement. Means already you have the rebar reinforcement, and this fibers is called as a secondary reinforcement. In the case of the high performance fiber reinforced concrete, if the volume fraction of fiber is higher than 2%, it only not improves the mechanical performance, it exhibits strain hardening behavior due to high fiber content, generally more than 5%. Anyone has any idea about strain hardening and strain softening behavior? We'll see. Strain hardening and strain softening behavior. So what are the types of fibers? Steel, plastic, glass, and other natural materials such as wood and cellulose. They are available in variety of shapes, sizes, and thickness. They may be round, flat, crimp, and deform. So this type of like see, these are the concrete aggregates. Suppose these are the voids, and these are the fibers. You see, these are the randomly oriented, right? These are the randomly oriented. So voids and microcracks serve as the crack initiators. That's why we have to be careful about the voids, amount of voids. Less the amount of voids, less the possibility to have the microcracks or crack initiators. So fiber presence prevents crack elongation and increase of crack width, increasing strength by the fiber spacing theory. So what happens? Suppose you have this type of voids, hmm, this type of voids, and you have one fiber from this side and one fiber from this side. This void allows some a certain amount of widening because of the crack initiation, and it allows up to this point. So this, it reaches the here and it reaches here. So what happens? Further widening will not allow by this type of fibers or this type of arrangement of fibers, right? But what happens if you have this here voids and here only you have the fiber, this side there is no fiber? If it is widening, do you think will it be resisted by the fiber? Whether will it be resisted by the fiber content or fiber matrix? No, because there is no fiber available from the other side. So widening will be possible from the other side. So that's why The orientation of the fibers or distribution of the fibers also has the main importance parameter into the design of the fiber reinforced concrete. Using of short fibers in concrete, most important, the fiber length of at least 1.5 times the maximum diameter of the aggregate. This is the thumb rule. Whatever the maximum size of aggregate you are using, the length of the fiber should be more than 1.5 times of that aggregate diameter. Then, hmm, right. Yeah, good question actually. There is a possibility because what happens, voids are not good. And if you see, the air entrainment concrete has a less strength compared to the normal concrete. Because if you are giving the, suppose you are testing, suppose air entrainment concrete and normal concrete under the compression testing, obviously because of the air entrainment, certain amount of voids are there. That will be allowing the crack initiator, and that crack initiator gives a less strength. So there is a chance to initiate the cracks in that one. So there is a more useful to use the fibers in that aspect, and people are using also because it will resist the further widening. Because there is a always possibility to have the micro cracks. Even we cannot see with our naked eye that micro cracks inside the micro cracking will happen. But because of that fibers, it will get resist. It will not further widening. Okay. Yeah. Now you can tell me, anyone, the here we are saying the length of the fiber should be 1.5 times of the diameter of the aggregate. So if, and here it is recommending that 30 mm fiber length will be there. So what will be the maximum diameter of the aggregate? Right, 20 mm. So in this case, they are recommending 20 mm of maximum size of aggregate. In that case, you can use 30 mm of fiber length. Fibers about 60 mm with a high reinforcing effect are used for slabs. Fiber reinforced slabs are also casted. In that case, 60 mm, that is longer fibers will be used generally. So what are the common characteristics of the fibers? Diameter 0.05 to zero point 0.5 mm. Length will be 5 to 60 mm. Aspect ratio is one of the major important parameter that is called as length to diameter ratio. Length to diameter ratio of the particular fiber, and that will be about 100. Now we'll see the mechanism, the bonding mechanism. You see, this is the fiber, this is the concrete matrix. Half of the fiber is embedded into the concrete matrix. That is we called as L by 2. This is the diameter of the fiber, and this is called as total length L. This is the tau, that is stress generating around surrounding the fiber. So stress, that is in Newton per mm square. This is the surface area you calculated pi d into L by 2. We'll get the force. Okay. So tensile force you are applying here, that is sigma into pi d square by 4. Okay. So if tensile force is more than the this parameter tau into pi d into L by 2, this characteristic strength, or sorry, not characteristic, this is the force surrounding the, or resisting force surrounding the fiber. If its tensile force is more, the debonding will happen. If resistance is more, the breaking of the fiber will happen, right? So that's why it is called failure by fiber in tension. When it is in tension, if this resistance is less and force is more, fiber sorry, the resistance is more, fiber and resistance is more and the tensile force is less, then fiber in tension will fail. But if resistance is less and tensile force is more, that interface in bonding, it will fail, or debonding will happen, and there is a rare chance the concrete itself will fail. So this is the tensile and this is the resistance force. So where sigma and tau are the tensile strength of the fiber material and the bond strength between the fiber and the matrix respectively. So you have to find out the first of all this bonding debonding properties of the particular fiber. So that's why you'll see if you are using if you see steel fibers also, it will have some of the hook. You'll find out the hook here or hook here, or any type of alternate arrangement like this zigzag pattern arrangement of the fiber. It will not, it is a rare chance to we will use the simple linear fiber. In the similar rebar also, you will have the tamp rebars, right? So that will go to the additional bonding of the concrete. So what are the advantages and disadvantages of fibers? Since fibers are generally distributed throughout the concrete, many fibers are inefficiently located for resisting tensile stresses. That's why I said distribution is very important. So spraying the fibers lead to 2D random orientation, whereas pre-mixing them during batching leads to 3D random orientation. Spraying in the sense, after the concrete prepared, we just spray the fibers over that concrete and then we mix with the some spatula or something like that. And pre-mixing means with the dry mixing itself we are mixing. That is called the random orientation, 3D random orientation. So efficiency factor to take care of the stresses depends on the fiber length, critical embedment length, and the orientation. Critical embedment length, this is the length. Here, whatever here it is L by 2, that is called as critical embedment length, and the orientation. Suppose you are saying here there is a no debonding of the fibers available possible for the L by 2 length, and then we provided another fiber into the same concrete matrix which is having the L by 4 length. So which will be will it be fail or it will be also resist the debonding? What do you think? We have here L by 2 length, another fiber here, suppose we have L by 4, which will be fail into the debonding? Obviously L by 4. L by 4, because what happens, whichever has the less embedment length or critical embedment length, that will fail first. That is, debonding will happen easily, easy to pull out. Even into the labs also, if you are seeing the normal rebar debonding test, in that case also, if the embedment length is less, the debonding will happen easily. Similar manner into the fibers also. So what are the different types of fibers looks like? These are the steel types of fibers. You see there is a hook type at the what we call the bottom and top, or extreme cases. Here glass fibers are there, polypropylene fibers, acrylic fibers, aramid fibers. Glass fibers are generally, what happens, this there is a possibility to have alkali silica reaction. So that's why we have to use the glass fibers, which is resistance to the alkali silica reactions. These are the carbon fibers. These are the wood fibers, wood cellulose fibers. There are different properties of fibers has been given into this table, that their diameter, specific gravity, tensile strength, elastic modulus, fracture strain. These three properties specifically, tensile strength, elastic modulus, and fracture strain, we should know before going for the any type of fiber reinforced concreting. Okay, so this is the in general idea about the fiber reinforced concrete. Now we'll see what is basically most of the um, constructions we are using the steel fibers. So can anyone tell me, we are using steel fibers? Is there any possibility to have the corrosion of the steel fibers? Why? Right, because we have the alkali present into the concrete matrix because of the carbon hydroxide, right? So because of that one, it will create the some oxidizing layer surrounding to the steel fibers, which will not allow in direct contact with the weather or the water. So that's why it is providing some protection against the corrosion. So steel fiber reinforced concrete. So addition of fibers reduces the workability. If it's very important when we are using the fiber content, you have to modify your mix accordingly. How we have to modify it? Because it reduces the workability. Why it reduces the workability? Any idea? It reduces the workability because specific surface overall specific surface area increases because of the length as well as the smaller diameter. And if area increases, specific surface area increases, more amount of mortar is required to coat surrounding of that matrix also, or fibers also, to get into the flow of that matrix along with the matrix that fibers. So more is required. So that's why more amount of higher cement content should be required, water should be required, sand content higher required for the same consistency compared to the normal concrete. Mixing, transportation, placing, and consolidation become difficult. Why it become difficult? Because we have to provide more mixing time. Transportation also we have to take care, and placing also we have to be take care. While it should not be onto the surface, it should be uniformly placed. Consolidation become difficult. Another important observation is that compressive and tensile strengths are not significantly affected by the fiber content, but flexural strength, bond strength, and toughness increase with the fiber content. The mix should be sufficiently cohesive to hold fibers without segregation. Sufficiently cohesive means higher fineness should be there, which can carry all the. Similarly, we saw higher fineness is required to carry the coarse aggregates along with the concrete matrix. Similar manner, here also higher fineness is required and higher consistency is required to carry all the fiber matrix or fibers along with the concrete matrix. There should not be a segregation happen in between the fibers and the concrete. So fibers increases the total surface area of the max mix, thereby increasing the demand for fines. For optimal performance, finer material content should increase with the fiber surface area. So how much it will increase? Here, the fiber area increases with the fiber dosage and decreases with the fiber size. With the fiber dosage, surface area increases and decreases with the fiber size. Total fine material. The range has been given, which is less than 300 micrometer. It is called as the total fineness material in the case of fiber reinforced concrete. That is cement, mineral mixtures, and fine aggregates. And it should be at least have the 400 kilogram per meter cube. We saw this type of range into the uh, self-compacting concrete also, where we called as the fineness of the material below which size of sieve. What is the size of? No, 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 no. 0.125 mm. Yes. Right. So the yes, okay, into the micron. 0.125 mm. No, I don't think so. 150 and 0.125, because hmm, yeah, but 1.5 is correct. But the range has been given. The recommendation is for 0.125, not 1.5. Hmm. So the high pH of concrete we saw protects steel fibers by forming a passive oxidizing film on the surface. This film prevents direct contact with the water and air, thereby avoiding corrosion of steel fibers. Some other key observations regarding to the mix of proportioning. Aggregate grading should be biased towards the finer side, means more amount of fine should be there. That is down to 75 micrometer. Use natural fine aggregate if unavailable. Improve grading by adding 4 to 8% of crusher fines. Increasing fiber content reduces fiber spacing, limiting the maximum size and proportion of coarse aggregates. Obviously, if you are increasing the fiber content, there is a more crowding of the fiber. So spacing between each fiber gets reduces. If more crowding, if you want to maintain the same consistency, the maximum size and the proportion, that is amount of coarse aggregates, we have to reduce to maintain the same consistency with the higher fiber content. Water demand content increases with the fiber content. How much it increases? Approximately 20 kilogram per meter cube per 1% fiber. This is a thumb rule. 20 kilogram per meter cube should water content should be increased per 1% of fiber. But it should not get go beyond 180 kilogram per meter cube. The range is in between 140 to 180 kilogram per meter cube. So accordingly, we have to made the changes into the our matrix or into the our concrete mix design by using some super plasticizer or any other admixtures. Water content should be minimized using water reducers, super plasticizers. How much? 0.4 to 1.4% of binder. Total cementitious contents may be increased. How? That is powder content it can increase. Fly ash content. High water content and sand aggregate ratio may you cause bleeding and segregation. So that's why to avoid the segregation, we can use the viscosity modifying agent as a admixture. Similar we have used into the cell compacting concrete also. Mixing for fiber content 0.5 to 2%. Normal mixing methods can be used with thorough mixing. Normal mixing method means whatever the mixing we are doing for our traditional concretes. Similar mixing method we can use it. Dry run, then we are adding the water plus SP content with together or different manner. But mixing time will be higher. That's why it's saying thorough mixing. Thorough mixing means mixing time will be higher. Mixing energy may increase by 2 to 4 times. Force action mixers. Force action mixers means RPM will be the high. Then we have to be take care about the uniform dispersion of the fibers also. For that purpose, dispensers, bundle fibers with water soluble adhesives also can use. Then fibers are added in a truck, agitating truck. Concrete should be mixed at high speed because that fiber should not get settled down. For that purpose, mixing should be the higher into the agitating trucks also. Mixing time for fiber reinforced concrete is typically 15 to 25% higher than the plain concrete. Mixing efficiency depends upon mixer RPM, wear of blades, fiber type, and dosage. Longer fibers and higher aspect ratios increase the risk of fiber balling. What is fiber balling? If mixing will not happen properly, not having the proper mixing speed, there is a possibility to have the settle down the fibers. And if the dispersion of the fibers will not proper, the fibers will intact each other close together and it will create the ball like structure that is called as fiber balling. So that's why dispersion is very important and it is higher possibility in the case what longer fibers and higher aspect ratios. Aspect ratios means length to diameter ratio will be higher there and the longer fibers. There is a possibility to have the fiber balling. That's why there is recommendation to use the short fibers into the apart side, in the slab. Only in the slab only they are recommended for the longer fibers. But in the case of the other concreting, short and discrete fibers, you can use it. Low workability mixes require longer mixing times to avoid balling. Adding fibers before sufficient aggregates are present may lead to fiber clumping. So fiber clumping means it will close together and intact. So to avoid that one, fiber aggregate should be there, which will create the space between the fibers and will not allowing to close together, increasing the distance between the fibers. So that's why aggregate sufficient amount of aggregate should be available into the fiber reinforced concrete. We cannot only go with the fine aggregates. Okay, pumping, obviously viscosity will be high because of the fiber content. So that's why pumping pressure will be high compared to the normal concrete. Pumping layout may be different because of the, if you are using the steel fibers, there is a possibility of the wearing, tearing of the pipe. So that's why pipe material, diameter, and wall thickness should be selected carefully based on the placement conditions. These are the important factors we have to consider apart from the normal concreting because of the inclusion of the fibers. Then how to check the homogeneity of the fiber dosage? For that purpose, one test has been recommended. You prepare the mix of the fiber, you get the some amount of the mix, hmm, known volume of the mix. Then 5 sieve is there. You put all the that fresh mix over that sieve. Then you remove the fibers are separated and dry and weigh. And whatever the weight you are getting, whatever the suppose 1 kg you use fresh mix, out of that one suppose, and you are provided 1% of the fiber, and you are getting, with respect to that one, average fiber content should be greater than 90% of the specified dosage. 1%, so 0.9 percent should be there into that fresh mix. Okay, then only we can say the homogeneity of the fiber dosage will be good. Fiber can be extracted using magnet or electromagnet. This thing will be possible in the case of only steel fibers, which can be we can remove or we can get it from the fresh matrix. For hardened concrete, core extraction and crushing, you can get it and then you can weigh and check the average fiber content from that one. So what are the fiber properties ultimately into the hardened state we have to see? We saw up to the fresh properties, mixing, because we saw all these things. Now we have to see how behave in the case of the hardened concrete. Mainly the fiber reinforced concrete uses with respect use into the hardened concrete, increasing the tensile strength, increasing the toughness, altering the failure mode. Now we'll see how it is altering the failure mode and that all things. First of all, we saw concrete matrix, water cement ratio, maximum aggregate size, and sand aggregate ratio affects the fiber reinforced concrete properties. Fibers, type of fibers, shape, size, length, and diameter or aspect ratio, then proportion affects, and fiber orientation and dispersion. Similarly, we saw voids is there. If the two fibers surrounding the voids are there, that can crack, that can reject or that will not allow the widening of the crack. But if the fiber is only on one side of the void, that will not possible to resist the crack of the widening. Then in the case of the steel fiber concrete, fibers characteristics, length will be 20 to 60 mm, diameter may be zero point 0.3 to zero point 0.9 mm, aspect ratio, that is length to diameter ratio 30 to 100, fiber content 0.5 to 2% by volume, that is 40 to 160 kilogram per meter cube. Maximum content is given 160 kilogram per meter cube. Fiber may be mixed directly into the mixer, that is with the dry mixing or spray. But into the spray, we have to be take care. It should be properly dispersed. It should not be on the surface. Added at the end in agitated truck. If it is in the RMC plant, agitated truck, you can add it at the end also, because the mixing speed will be high compared to the normal concrete. So that can be also possibility to properly mix with the concrete into the providing with the agitated truck. Workability. So addition of fibers reduces the workability. We saw because of the increase in the overall specific surface area. Higher sand to aggregate ratio may be required as fiber aspect ratio increases. Sand to aggregate ratio means indirectly we require the higher fineness content. That is sand content. We require higher. Mixing becomes more demanding with increasing fiber content. Suppose for 0.5% fiber content, 1% fiber content, 2% fiber content, you will require a higher mixing energy and mixing speed for the higher fiber content, that is 2% content compared to the 0.5 and 0.1% fiber content. Mechanical properties: steel fibers carry tensile stress only after cracking. Tensile strength of the steel fiber reinforced concrete is approximately equal to the cracking tensile strength of plain concrete. See, this sentence you can see, tensile strength of the steel fiber reinforced concrete is approximately equal to the cracking tensile strength of plain concrete. Then compressive strength is mainly governed by water cement ratio, similar to normal concrete. It is not at all governed by the fiber content or the fiber type. Compressive strength is not at all dependent on the fiber content. It only depends on the water to cement ratio, whatever we saw into the earlier classes, the one plot that is dependent on the water cement ratio. I hope you remember that plot, water cement ratio versus compressive strength. So anyone remember the slump value or slump uh, value is dependent on what content, on what parameter? No, water cement ratio, compressive strength is dependent on water cement ratio, but slump, we saw two plots. Slump is dependent on the water content, unit water content, and compressive strength is dependent on the water cement ratio. So addition of fibers does not significantly increase the compressive or tensile strength. So what it improves actually? It improves post cracking behavior, which is more important. We'll see with the plot also how it is improves. Flexural strength, bond strength, and toughness increases with the fiber content. Fiber becomes effective after matrix cracking. Then only fiber will come into picture. When fiber will come into picture, we have the concrete beam, suppose, and once beam first crack appears, then only fiber fibers what we called effectiveness come into picture. So post peak behavior or post cracking behavior is the primary advantage of steel fiber reinforced concrete. So what is the key takeaway from these observations? Fibers do not significantly enhance pre-cracking strength but greatly improve post-cracking performance, ductility, and toughness, making steel fiber reinforced concrete fundamentally different from the plain concrete. So how we will see, similarly for normal fiber reinforced concrete also, it improves tension, flexure and shear, enhance crack resistance, ductility, impact resistance, high crack arresting capability, leading to reduced crack width and improve fatigue strength. What is fatigue strength? What is mean by fatigue? Fatigue fatigue load means you have certain suppose you have the certain not exactly reversal of traces, continuous, you can say continuous loading means suppose you have a one beam and if you want to test for continuous for suppose 1 kilonewton, so in the cycles, continuous cycles are going 1 kilonewton for 1 second, 1 kilonewton for each second load is coming, that is called fatigue strength, or the resistance against that one is called fatigue strength. So that is also improved with the help of the fibers. So compressive toughness at failure, high flexural toughness in bending, and improve resistance to impact and explosive loads. Impact and explosive loads means in the case of military operations, you require the blast resistance structures. In that case, particularly, so fiber cement bond properties. We saw interfacial bond characteristics and fiber debonding behavior play a critical role based on the embedment critical length. Whatever the amount of length available into the concrete matrix, based on that one, interfacial bond and debonding will observe. Two analytical approaches to describe the fiber debonding. We'll not go much detail about these analytical approaches, but Two are there. One is stress-based criteria, another one is energy release criteria. What stress-based release criteria shows? Debonding occurs when interfacial shear stress reaches a critical value. We saw that one, that uh, uh, explanation we saw, that L by 2 length and then tensile strength and uh, resistance strength. So that is stress based criteria. Energy release rate criteria: demanding propagates when supplied energy exceeds interface resistance energy. We have a certain amount of interface resistance energy and a certain amount of tensile stress energy. So based on that one, energy release criteria has been developed. Bond properties are commonly evaluated using single fiber pull-out test. Similarly, for the bond pull-out test, will do for the rebars for the single bar only. Here also, single fiber pull-out test will do. But in the case of the fibers, you need equipment which has the least count. Maybe up to, in our institute, so it has been used 25 kilonewton UTM to see the fiber pull-out test, because higher range equipments you cannot use. Similarly, we are using for to the rebar, and you will find out with the help of the this 25 kilonewton UTM, you will find out the pull out single fiber pull out test, and based on that one you will see the strength stress based criteria or energy release rate criteria. So how post peak behavior changes, you will see. So this is the normal concrete. This is a stress versus strain graph. Once you are loaded, this graph, once first single crack appears, the graph will go down like this for the normal concrete. But in the case of the fiber reinforced concrete, the crack will happen, then fiber pull out will start from here, and the post peak behavior will show this fiber reinforced concrete. It will not suddenly fail, but normal concrete will fail like this only. So that's why fiber pull out test is very important, and here this shows the fiber pull out here. Interface property is also important. And if you are having the higher amount of fibers, what happens? First crack you will appear here. After that cracking, multiple minor cracks will happen. This multiple cracking region. Hmm? That multiple cracking region will give the minor cracks, but will not allow the specimen to get fail. And after some time, multiple cracking, then fiber pull out will start here, and each fiber will get pull out, and then specimen will get fail here. So means the this fiber reinforced concrete allowing more life basically, or more resistance to the load compared to the normal concrete. So what effect of addition happen on the tensile properties? Fibers improve tensile strength. You see this graph, tensile stresses, this is the normal concrete, and this is the only 0.5% volume of fiber reinforced concrete, but tensile stress is higher than the normal concrete. So that's why tensile strength increases, toughness, area under this curve, failure mode also changes. So strain softening, when it is happen, if fiber volume is less than 1%, single dominant crack, higher energy absorption than plain concrete. Strain hardening, higher fiber volumes, that is more than 1% or more than 2%. Multiple cracking we saw into the last image also, and significant post cracking load carrying capacity. As compared to the concrete, both are greater than normal concrete. Normal concrete will not show any strain softening behavior or strain hardening behavior. It will directly go down that curve we saw here, directly go down. This is the strain softening behavior actually. Strain hardening means graph will go like this up. We'll see next graphs. So what is the key takeaway from here? The primary advantage of fiber lies not in increasing the peak strength, but enhancing post-cracking behavior, toughness, crack control, and energy absorption, governed largely by fiber matrix bond and fiber dosage. Here you see the fiber content goes on increasing. There is a First, you can see up to two. This one is 2%. It may be the critical for the in between the strain softening and strain hardening. Below that one, you will see this graph will come like this below 2%. Above 2%, you will see the graph nature is going up like this. That is called the strain hardening. What it is called? Strain hardening, which is more useful in the case of the uh, what we call the flexural specimens. Another, this strain hardening behavior, this plot you can see is divided into four stages: stage 1, stage 2, stage 3, and stage 4. Stage 1 shows elastic response of the composite with few micro cracks. This one. Stage 2, distributed crack localized to form the first major crack. Here you will observe the first major crack at the point of B. Then load is transferred through the fiber matrix bond. A matrix cracking occurs when matrix tensile strength is exceed. Means this first crack appears. So whatever the fibers will available in between that first crack will start to resist that crack widening, and because of that one surrounding there is a small amount of micro cracks will increase or multiple cracking will happen in between the area B to C. Then stage 4, no further matrix cracking happen and load is carried only by fibers until tensile failure. What is tensile failure? Means fiber will itself get breakdown. Mm. Yes. Right, right. Mm. Okay, you are saying specifically if you the cracking will happen at the bottom means you can put only fibers at the bottom. Yeah, yeah. Center means not starting from the bottom or directly at the center. You are saying. Yeah, it's depend on the loading condition. If you are going for the 3 point bending test, 4 point bending test, or depend on the loading conditions, it will happen into the shear or it will happen into the flexure. Depend on the loading condition. But it obviously the crack will start from the bottom only because into the flexure. Hmm? But what happens if you are not providing the fiber matrix in above area also? You are only providing into the bottom. No doubt it will resist the bottom widening. But after some times, what happens? The bottommost fibers gets tensile breakdown happen. Then that further widening will resist by the above fibers, not exactly at the top fibers, but into the middle fibers also. Yeah, it will not tension, but I hope I will show one image after the lecture. So the beam will not exactly crack. It will not exactly broke down. It will resist too much energy or too much absorption of energy happen because of the fibers. Suppose bottom fibers broken down or into the tensile, the top above that one, whatever the fibers will be available, that will resist. Then if it is that breakdown, above that one. So it is a continuous process of the widening of the cracks until all the fibers from that matrix itself goes breakdown. So it will. That's why it is giving this micro cracking B to C region and C to D region because of the multiple fibers, not because of the bottommost fibers. Okay. Then another aspect of the behavior fiber reinforced concrete, you'll see some of the like this is not actually the beam. This is some of the like a payment type of thing. If you see this is according to the IRC SP 46 2013. They want to see the post cracking response. So payment design also most of nowadays they are using the fibers. So along with the main reinforcement. So deflection curve 3-point bending test has been given Indian Road Congress SP 46 2013. Larger deformation reasonably at high stress resulting in larger area under the stress strain or low deflection curve given by the fiber reinforced concrete. So toughness, we saw the debonding, cracking resistance, widening resistance, that all things. Now, what is the toughness? Toughness in bending. The area under the load deflection curve is used as an index to estimate the energy absorbing capacity. That is called toughness of the material. So, whatever the area under the load deflection curve, that is estimate the energy absorbing capacity, and that is called the toughness. So why toughness is required? Because it improves the resistance. If toughness is higher, fatigue resistance, impact resistance, and impulse loading will be the higher. And toughness is higher, we also indirectly say that it is a better ductility, which will be good in the case of the ductile resistance. So how we will calculate as the toughness index? Different code given different aspects of the calculating the toughness index. So to characterize the toughness index into the bending, the ratio of the area under the load deflection curve up to a specified deflection to the area up to a first cracking, or simply the area under the curve up to a specified deflection. Means this is the graph we have, total load versus deflection for the fiber reinforced beam, and this is the unreinforced matrix beam, this one JKL. Okay, so definition of a toughness index is that area O A B EG, that is up to specified deflection, up to 1.9 mm deformation, you calculated the area under that curve, then area under the OAJ, this one, that is called the toughness index according to the ACI. Another definition according to the ACI only, OABEF means tensile failure of the fiber, up to the tensile failure of the fiber, and area OAKL, total deflection curve of the normal concreting. So that ratio gives the toughness index. But in the case of the Japan Concrete Institutes, what it says, they directly says toughness index is the area of the load midspan deflection curve up to the value of 1 by 150th span. Suppose you have a span of 5 meter divided by 150, whatever the deflection you will get it, whatever the delta 150 value you will get it, that value will point out here, and the area under that curve will be the your toughness index. So we saw toughness index, we saw all the fiber reinforced properties, types of fibers. So what we get it from the here, fiber reinforced concrete improves strength in tension, flexure and shear, enhance crack resistance, resist crack widening, improves ductility, impact resistance, high crack arresting capability. That's why post peak or post crack behavior is more important. Reducing crack width, increasing fatigue strength, compressive toughness at failure, high flexural toughness in bending, and strong resistance to impact and explosive loads, particularly into the military operations structures. Where we can use the fiber reinforced concrete, it may be used into the pavements and tunnel lining with reduced thickness, tunnel linings without conventional reinforcement by increasing fiber content, improve resistance to freezing and thawing, enhance durability. Someone has asked about the freezing thawing, here. There we have voids. That's why fibers are used, right? Yeah, yeah. Increase shear capacity of structural members. In it is also used in the shotcrete, but shotcrete, as we have to spray the concrete, we always use small length of the fibers. That is called short fibers, more workable but less effective individually in reinforcement. Fibers of 20 mm or less generally used. Length will be 20 to 60, and aspect ratio of 30 to 80. So this is the brief overview of weak 6, that is mostly about the fiber reinforced concrete and short introduction about the rheology. So I hope I'm able to give some overview on this one. So if anyone has any doubt, please let me know. Otherwise, we move forward with the questions. Okay, we'll move with the questions then. So the first question is, in the context of flocculated suspensions, consider the following statements. Statement 1, stress corresponding to the breakdown of flocculated network is called yield stress. Flocculation of colloidal particles, that is particles smaller than 1 micron in diameter, results in the formation of gel. So what will be the answer? Both the sentences we saw into the brief overview. Both are true. Okay. Any other answer? Okay. Any other? Both the statements are true actually. We saw both the statements into the brief overview also, because stress corresponding to the breakdown of flocculated network. Flocculated network which has the internal forces but weak internal forces. That's why smaller amount of force allows to break down that force, and that smaller amount of force is called as a yield stress. And second statement is flocculation of colloidal particles, that is particles smaller than 1 micron in diameter, results in the formation of gel. That is a recommended statement from the code itself. Second question, consider the following parameters in the context of concrete: tensile strength, early age compressive strength, toughness, and workability. So which of the following correctly identified factors of concrete that are improved with the use of fiber reinforced concrete? Which are the factors we can use improve with the fiber reinforced concrete? 1 and 3. Right, right. Because tensile strength and toughness we are increasing. Next, regarding to the rheology, statement 1 says rheology is the scientific study of the deformation and flow behavior of materials that exhibit time dependent responses to applied stress. Statement 2 says the rheological properties of fresh concrete govern its workability, influencing the methods of processing and placement. So, what will be the answer? Okay, any other answer? Okay, so answer is both are true, because rheology is a time dependent. We saw now, because of the hydration, yield stress goes on increasing. I said the one example that 0 minute, 5 minute, 10 minute, 15 minute. Every time we will get the different yield stress because of the time dependent response, and the time dependent response come into picture because of the hydration mechanism. So both the statements are true. Next, if a matrix contains steel fibers constituting 1% of its total volume, with each fiber having a diameter of 0.5 mm and an aspect ratio length to diameter, that is 75, determine the total number of fibers present in 1 cubic meter of the matrix. Calculate this one. How will calculate? 1% of total volume. Hmm? Not able to listen. Can you please repeat it? 1% means 0.01, right? Total volume. Yeah, because every time we'll go with 1 meter cube only. So diameter of each fiber is zero point 0.5 mm. Aspect ratio is 75 mm. Aspect ratio means L by D. First of all, write down all the parameters what we have given. We have given total volume. If matrix contains steel fibers constituting 1% of total volume. So means VF is given, right? 0.01. Diameter is zero point 0.5 mm. L by D is 75. So we have D also, we have L by D also. So we can calculate the length. So what will be the length? We have L by D ratio, that is 75. Then we have diameter zero point 0.5 mm. Convert it into meter if, and then 75 into 37.5 mm. So 37 point, convert it into meter. Zero point 0.5 into the zero point 0.5 into 10 raised to minus 3. So 75, 37.5 into 10 raised to minus 3 meter. That is the length we'll get it. Now calculate the volume of the single fiber. What will be the volume of single fiber? Yeah, calculate. Tell me the value of that one. Convert it into meter cube, and then in meter cube you can tell me the value. 0.01 what value volume? No, no. We got the length 37.5 into 10 raised to minus 3. So calculate the total. First of all, one fiber volume. So one fiber volume is equal to pi r square into L. So or so R you can get it 0.5 by 2, 0.25 into 10 raised to minus 3 square into L. L is we are having 37.5 into 10 raised to minus 3. Right. Then total fibers is equal to VF into V matrix. Hmm? Right, 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 right. Any other got the answer? All came up to fiber matrix volume of the single fiber matrix. VF is equal to pi r square into L. We have the L value. R is the radius. You can get it 0.5 by 2 into 10 raised to minus 3. You can calculate the single fiber volume, that is 7.363 into 10 raised to minus 3, sorry, minus 9 meter cube. Then total fibers is equal to VF into V matrix. Total fiber matrix or total fiber volume, that is 0.01 into 1 meter cube. VF 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 कितना था? VF is equal to 0.01, right? And V total fibers we have to calculate. So V total fibers is equal to VF into VF into V matrix. V matrix how much it is? 1 meter cube. So 1 into 0.01, how much it is? 0.01. Simple. Then n, number of fibers we have to calculate. N is equal to V total upon V total upon V single fiber, volume of single fiber. So how much single fiber you got it? So okay, so 0.01 upon 7.363 into 10 raised to minus 9. Calculate, you will get the value of n 1358122.181. Understood or not? Everyone understood? I think some of you got, yeah, some of you got answer, right? Okay, then we'll move forward if you are satisfied with the answer. Okay. So next question, in the context of fiber composites, consider the following statements. Utilizing moderate fiber volumes in composite enhances their mechanical properties. Incorporating low fiber volumes in composites mitigates shrinkage, reduce induce cracking. What will be the answer? We saw the fiber volume that three zones, less than 1, 1 to 2, and greater than 2. So what it indicates, statement 1 and statement 2? Both true. Okay, correct. Both are true. Because moderate will be responsible for improving the mechanical properties, higher will responsible for the post cracking behavior and stain hardening, and low volume fiber only for the shrinkage induced cracking resistance. Next, related to the previous one, self compacting concrete, flowability can be achieved by increasing the water powder ratio. Addition of superplasticizer imparts cohesion in the SCC. We already saw this question into the last session. What will be the answer? Both. Okay. Any other? Answer 3. Okay. Any other? I think all are wrong because flowability can be achieved by increasing the water to powder ratio. Water to powder ratio means water increasing, powder ratio if it's keeping constant, or otherwise you are keeping water constant, powder we are decreasing. So automatically flowability will get increased. And addition of superplasticizer increases the flow. It's not does not improve cohesiveness. For the cohesiveness, viscosity modifying agent is there, or otherwise you can improve the fineness content. These two you can do for increasing the cohesiveness. So that's why statement 2 is false and statement 1 is correct. Understood? Any doubt? Okay, no doubt. So next is in the context of fiber reinforced concrete. Statement 1, at higher volume fraction of fibers, the tensile strength of the matrix is reduced. And area under the deformation curve is higher in FRC when compared to the normal concrete. So what will be the answer? Okay, any other? Okay. First false and second true. Correct. Because tensile strength of the matrix improves. It does not reduce. An area under the deformation curve is higher FRC when compared to normal concrete is correct. Statement 1 is false and 2 is true. Next, in the context of FRC, statement 1, to maintain the same consistency, the sand to aggregate ratio must be lower than that of the conventional concrete. Statement 2, the high pH in concrete resulting from CSH gel formation provides corrosion protection for steel fibers. What will be the answer? Okay. Any other? Okay. One is false. Is your answer is that one true? Correct. But read second sentence once again. The high pH in concrete resulting from CSH. The pH content is not resulting from CSH. It is resulting from CH, calcium hydroxide. That provides protection for steel fibers. CSH doesn't create pH, improve pH. Only CH content improves pH and other alkali content. That's why statement 2 is also wrong. Because of here, this CSH gel doesn't provide any alkalinity. Okay. Because of only one word, sentence is wrong. The source of the enhancing pH is the CH, calcium hydroxide, not CSH. Understood? Next, in the context of fiber reinforced concrete, the maximum size of coarse aggregate remains unaffected by the fiber content. Second sentence, increasing the fiber proportion in the mix can reduce the required amount of fines. So what will be the answer now? Both are false. Okay, okay, both are false is correct answer because you see fiber maximum size of fiber or maximum size of coarse aggregate we have to reduce because of the fiber content. We cannot say it is unaffected because we should not have a more congested concrete matrix. Then increasing the fiber proportion in the mix can reduce the required amount of fines. No, we required more amount of fines because of the increasing the overall specific surface area and to carry all the fibers and the whatever the coarse aggregate along with the concrete matrix in the flow. So that's why both the statements are wrong. In the context of FRC, statement 1, amount of fines required in the mix could reduce if the proportion of fiber increases. Okay, if it is repeating it seems. Huh? Yeah, previous question and this question is same. Next, in the context of FRC, statement 1, debonding of the fiber from the matrix will take place when the maximum shear stress at the interface reaches a critical value. Statement 2, incorporation of fibers into concrete does not affect the failure mode. What will be the answer? Both statements are false. Okay, any other? Statement 1, you can read it once again. Debonding of the fiber from the matrix will take place when the maximum shear stress at the interface reaches a critical value. It is true because we saw that diagram, right? Embedded length and that all things. If both are critical, both are equally, there is a possibility through debonding, right? Shear stress around the matrix, what we call the fiber matrix, and that tensile stress, both are equal or that one. It is a possibility to have the debonding of the fibers. And second one is wrong because incorporation of fibers into concrete does not affect the failure mode. It's wrong because it changes the failure mode post cracking behavior. Okay. So first one is true and statement two is false. Next, in the case of FRC, first failure mode of fibers in FRC is independent of the length of the fibers used. Second statement, steel fiber reinforced concrete has higher tensile capacity compared to the plain concrete. So what will be the answer? Okay. Answer is third. Okay. First one is false, statement is true. I think most of the are saying that one only, right? The answer three is correct actually because the fiber length is important in the failure mode also because if the fiber length is very short, embedment length will be the less and the crack resistance will be the less. So appropriate fiber length will be there, should be there into the particular specimen for the particular use of the specimen. If you are using into the bending, little bit more length compared to the very short fibers, maybe 20 to 60 in that range will be required. So we cannot say it is independent of the length. It is dependent on the length. Hmm. Hmm. Yeah, it's actually here maybe the tensile strength into the capacity because this question I have took from the previous assignment only. So maybe they are saying tensile capacity in the aspect of the tensile strength because tensile strength we saw the graph is in peak tensile strength is improving. So this is like a subjective case maybe. Hmm. So this all questions from this week six. So I hope you got some overview of the week six lectures. If anyone has any doubt, please let me know, or then you can solve the assignment four also and now assignment six also. We have to solve two assignments, right? Yeah. So I think anyone has any doubt? If it is not there, then we'll end the today's class. Okay. Yeah. Yeah. Thank you so much, and yeah. Good night. Good night, everyone. Yeah. Thank you. Good night.